Okay, so in this particular video, we'll do some proofs here, derive a few functions based on what's given to us. Okay, all right, so let's do it. So here we have a football is kicked at an initial speed of v. So here in this diagram, that vector there, that is v, aka our initial speed, at some unknown theta. So here's your angle, and it wants us to derive all this A, B, C, D, E, and F. All right, so let's knock it out. Okay, so in part A, it says to derive an expression for the horizontal velocity component, Vx, in terms of V and theta. So again, in the diagram, we're given V, the initial speed V, and then the angle here is theta, and it wants us to derive an expression for this horizontal component, so which is pretty easy to do. Okay, so all I'm going to do is I'm going to just carry down this vector V here in my work. That's going to be V. And then I'm just going to draw my right triangle. So that is going to be my Vx, and this is going to be my Vy. Okay. In the schematic, Vy is drawn on the left side, but because it is a vector component, I can move it left or right without tilting it, and it doesn't change the magnitude or the vector itself. So I'm just going to move that Vy over here just to complete a right triangle. So it doesn't really matter how you draw it, just so you know. Okay. Here's theta in the diagram. So therefore, here we have a right triangle, and we are given the direction as some unknown theta. So to do part A, all we have to do is use cosine. The definition of cosine is adjacent, which is Vx, over hypotenuse, which is our vector V in this case. Okay, so a cosine of theta is adjacent, which is Vx, over hypotenuse, which is V, and therefore to find Vx, we simply multiply both sides by V to get Vx by itself. In doing so, Vx then is equal to V cosine theta. Okay, so that's our answer for part A. Now let's do part B. Part B asks us to derive an expression for the vertical velocity component Vy in terms of V and theta. Again, in the image, in the given schematic, Vy is drawn on the left side, but here I have my Vy on the right side, which is the same thing. I like to draw it on this side because it makes a perfect right triangle. So therefore, Vy is your opposite relative to this theta or perspective. So therefore, I'm going to use sine. Sine of theta is equal to opposite, which is Vy, over hypotenuse, which is V. So therefore, sine of theta is equal to Vy over the vector V. And if we solve for Vy by doing the same algebra step as previously in part A, multiply both sides by V in the denominator there. Therefore, that cancels out. In doing so, we have V sine theta is equal to Vy. So this is our expression for Vy. Okay, so that's A and B. Part C asks us to derive an expression for the time that it takes to reach the peak of the flight. So time for the peak of the flight is not bad. Okay, here I have my average acceleration equation. Instead of A, I just replace it with G due to gravity, aka acceleration in the y direction. Therefore, I would write Vfy minus Viy over the change in time, because by definition, acceleration is the change in velocity over a certain amount of time. Okay, but since it asks for the time at the peak, I know that at the peak my Vfy is 0. So in solving for t, I'm going to just flip-flop delta t up to the left, and I'm going to move g down to the right in the denominator. I'm going to cross out Vfy because it's 0 at the peak. Therefore, I can just substitute Viy, and Viy is already calculated in part B. Vy or Viy here is simply V sine theta. So wherever Viy is, I can substitute it in for V sine theta. Therefore, I just have negative, which is part of the function that I haven't canceled out yet. There's negative, that's going to carry down. And Viy can be substituted for V sine theta, which is here in the circle, and then divided by G. Now, it's important to note that G here would be a negative 9.8. So therefore, the negative sign and the negative and the negative 9.8 will cancel out, which will give us a positive quantity because time is a scalar. Okay, so that's that. So that's the expression to find the peak time. All right, now let's do part D. Part D asks us to derive an expression from the maximum height h. In this diagram, it calls it h. You can call it h max, y max. It doesn't really matter because the math is what we're trying to do here. All right, so in terms of v and theta, we can start off using this particular kinematics equation. Why? Because we know that VFy at the peak is 0, which eliminates one of them. And we already know VIY and we know G. And then delta Y here can just be substituted in, for H. So delta Y here, it got replaced for H, or you can keep it as delta Y, doesn't really matter. VIY got substituted for V sine theta. So if you kept up with the work for part C, Vy is V sine theta. So VIY is just V sine theta. And then the square remains on the outside of the parentheses here. I'm just going to distribute the exponent to both the V and the theta. And then I'm also going to go ahead and move the 2G down in the denominator because I'm trying to isolate for H. Okay, so a little algebra step here, a little distribution, and then voila. V squared sine square theta all over 2G, and that is our expression for H max. The negative sign there, it doesn't really matter. If you want to keep it there, if not, take it out. But keep in mind that that will dictate whether you plug in G as negative 9.8 or positive 9.8. If the negative sign is there, you plug in negative 9.8. Okay, if the negative sign is crossed out, then you would put in G as positive 9.8. This particular problem height is positive, so you can't have a negative value. So be careful with your sign for G. Make a choice. Do you want the negative sign there, or do you want to leave it out? If you do, plug in positive 9.8. Okay. All right, let's do part E. It says derive an expression for the horizontal range, in this case, in terms of V and theta. So in this diagram, horizontal range is from all the way left to where it lands on the ground at the same level. So this is important to note that the ball lands at the same level from which it was kicked. Okay. Our horizontal displacement function is delta x equals Vx times time. Now, it's important to understand that which time you need here. Since R represents the horizontal distance from start to finish, I need to use the total time. Okay, so it's important to use the proper time, otherwise you will run into an expression that is incorrect. Here, Vx can be substituted for, oh, I got excited. I just wanted to point out, reminding you that if you didn't keep up, T at the peak in the previous part is negative V sine theta over G. Therefore, I did this for you just so it helps. T total is simply 2 times the T peak because due to symmetry, okay? So T here, my work, is going to be T total. Therefore, I can just substitute real quick. Vx is just V cosine theta. T here is T total, which is just 2 times the T to get to the peak. And I highlight the V's here because now we have V times V, which would give us V square. And then 2 times cosine times sine just gives us 2 cosine sine. And then all over G, because the only thing in the denominator is just G. So I carry that work down. I highlighted this 2 cosine theta sine theta because this is a double angle identity. Okay, so here's the chart of all this stuff. You can Google this if you like, or hopefully your trigonometry is solid. Sine of 2 theta is equal to 2 sine theta cosine theta. I know I wrote 2 times cosine times sine, but 2 times sine times cosine is the same as 2 times cosine times sine. You're multiplying here, so the order in which you write the function here doesn't matter. Again, so you can say 2 cosine sine, or the way it has it here is 2 sine cosine. It doesn't really matter. All that is equal to sine 2 theta. So therefore, I can substitute 2 cosine sine for sine 2 theta. Okay. So this is a quick substitution. So the double angle identity allows us, instead of having cosine and sine, we can just rewrite it in terms of just sine. But it's sine of 2 theta. This is known as a double angle identity. All right, and that is our function for the range. But I do want to point out here that this function is often misused if you don't pay attention, okay? This particular function is only good if delta y is equal to 0, okay? Delta y is equal to 0 allows us to use the total time as double the time of the peak. Otherwise, this statement would fall apart, okay? So T total is only twice the time to get to the peak because it starts at the ground and it also lands on the ground due to symmetry. So you cannot use this range function to find horizontal displacement for other problems that fall farther than where it starts. All right, so keep that in mind as you practice. Let's do part, this is not part A, this is part F. Sorry, let me just fix this real quick. This bullet should have been part F, not that it matters. All right, so It wants us to find the ratio for h over r for when delta y is equal to 0. So here we have r, and then it just wants us to do a ratio for h over r. So h, according to my work in the previous parts, is negative v square sine squared theta over 2g. And then r, we just found in part E, okay, which is negative v squared sine 2 theta over g. So you notice here these two functions look really similar, okay, but you have to be careful. The h function has a sine square, while the range function has a sine of 2 theta. The h function has a 2g in the denominator, while the range function only has a g in the denominator. You got to make sure you know your functions well before you leave out certain things or introduce certain things that are whack, okay? So here I can just do a little bit of manipulation. I have a fraction divided by another fraction. So in math, having a fraction divided by a fraction is the same thing as multiplying by the reciprocal of the bottom fraction. So instead of having negative v squared sine 2 theta over g, I'm just going to multiply it by g over v squared sine 2 theta. And here we can just cancel out a few things real quick. I see a negative v squared. I also see a negative v squared, so I'm going to cancel it out. I see that there's a g on the top, and there are two g's on the bottom, so I'm just going to cancel just a g in the denominator. And then I'm just going to rewrite sine square as sine times sine. Okay, so hopefully you're keeping up with substitution. Instead of saying sine squared theta, well, sine squared is just sine of theta times sine of theta. And then I want to undo sine 2 theta. Because I can undo sine theta just so that I can cancel sine in the numerator. So instead of saying 2 sine 2 theta, I can carry the 2 over, but sine of 2 theta itself is 2 cosine sine theta. So I can cancel sine out, okay? And I can cancel the sine on the bottom out. So the only thing left in the numerator now is just sine. Okay, but here on the bottom though we have 2, which is this coefficient 2, and then sine of 2 theta introduces another coefficient 2 as the double angle identity. So 2 times 2 is 4, and then the only trig function left here on the bottom is cosine. So we can simplify this. H over r is sine theta over 4 cosine theta, but then sine over cosine is just tangent in trig. So instead of saying 1 over 4, I just factor out 1/4. Okay, instead of saying sine over cosine, I just substitute sine over cosine as tangent. So the ratio in this case is 1 over 4 tangent of theta, whatever theta is for this particular problem, for any particular problem. All right, I hope that helps in terms of understanding how to do certain proofs. All right, good luck. Stay nerdy, don't be whack.